S.P. Arsaf from Mechanical and Engineering Department, IIT Roorkee. In the previous lecture, we discussed about the 2 degrees of freedom systems, that how the damping or the masses or the stiffnesses are being varied when we are taking the 2 degrees in that. We discussed about that how the eigenfrequencies can be calculated when you have the 2 degrees and how you can make the coupled equations in that. And we know that when the system is in the 2 degree of freedom systems, there are 2 natural frequencies which are simply a reflection of our characteristic roots of the equations, and then we have the corresponding mode shapes for that. And these mode shapes are absolutely reflecting individual natural frequencies for that. And then also we discussed about when you have a damping involved in that, then certainly we can simply calculate the undamped natural frequency and the damped natural frequencies for that. Lately we solved some numerical problems for along with these kind of concepts. In the today's lecture, again we will further carry out the similar kind of features, that if we have the 2 degrees and more than 2 degrees of freedom system, generally we are referring more than 2 degrees of freedom system as the multi-degree of freedom system, then how the things are being varied along with the masses or the stiffness or the damping for the higher degrees, like the natural frequency or the eigenvalue or the eigenvectors, that means the mode shapes. So in that same we are taking the same previous numerical problem in which the 2 masses are simply under the oscillatory motion, which are being constrained by this spring motion. So we know that when you have more than 2 degrees of freedom system, there are here the matrix formulations for making the equations of motion, and these matrices are simply reflecting that how, what kind of arrangements are there, and according to the system arrangements the elements are being coming into the matrix formulations. So the matrix formulations even makes it possible to solve the system differential equations using any kind of the solving techniques or the software particular. We need to first go to the basic equations like the inertia force, the damping force, or this the restoring forces, and when it is being excited by external forces, we can simply go to the Newton's law. So you can see that the equation 1.26, which is simply the reflection of the same equation but only in the state space form, or we can say only it is in the formulation of the matrix. You can see that the mass matrix is there, which is nothing but the symmetric matrix along the diagonal, and it has to be. If there are some problems in the formulation, it seems that the whatever the degrees of freedom or whatever the formulations are not being captured correctly. So you can see 1.27 is nothing but showing the mass matrices along, and it is the symmetric along the diagonal M1 and M2. And even if you are going for higher degrees, it should be in the same manner only. Even if you just see the damping or the stiffness matrices, they are also in the similar manner only. But again, if you just see the diagram, that what exactly the diagram was, so that we can straightaway understand what the feasibility of the system arrangement is, you can see that we have the 2 masses on which the 2 simple harmonic motion is being there along with the displacement x1 and x2, and the forces are being acted on that F1t and F2t. And with this we have the stiffnesses K1, K2, K3, we have the damping C1, C2, C3, and then all these the motions are being occurred accordingly. So now if we want to just formulate this, we know that the damping matrices is exactly in the same way just we derived the stiffness matrices, and they have to be positive along the diagonal only. If any negative factor is coming along the diagonal in the damping or the stiffness matrices, that means there is some problem in calculation, or there are some problems in the formulation of these features, either in the free body diagrams or in capturing those forces with these elements. So you can see 1.28 equation is just reflecting that how the damping is being varied. Like the first element, it is here, as you can see in the diagram, the M1 is in between the C1 and C2, so certainly the damping is straightaway playing a key role in that. So in the first one it is C1 plus C2, and then on the second side it is minus C2, and then here our mass M2 is also varied in between the C2 and C3. So certainly we have on one side it is minus C2 and on other side it is C2 plus C3, and the same manner is coming in the stiffness matrices as well, because the arrangement of our damper and the spring stiffness are in the similar manner in our previous diagram. Then there are two displacements of the mass 1 and mass 2. So certainly we have the mode shapes after being displaced by the F1 and F2 the forces. So what we have x of t, which is nothing but a reflection of our displacement outcome is x1t and x2t of two manner, and the same forces which we are applying, the input forces, are F1 and F2t in the matrix form. So now you see here, since we know that excitation forces are simply producing your homogeneous solution using the particular integral, or we can say this is something which like we want, because we know that the complementary function is non-homogeneous, simply giving you the this transient feature. Our main part here is to calculate the steady state feature, which is simply bounded by this forcing factor, or we can say a particular solution. So with that, you see here we can say that our force input F1 and F2 are simply showing the simple harmonic motion. So we have F1, which is like the time bounded the forces. So it is F1 e to the power I omega t. The force 2, which is acted on mass 2, is nothing but equals to F2 into e to the power I omega t. So we have both the forces, and then we can expect the outcome in terms of the steady state formulation, or we can say the particular integral. So x1 p is nothing but equals to x1 p, which is the amplitude, into e to the power I omega t, which simply shows the simple harmonic motion in the outcome. Similarly, x2 p, which is related to the displacement of mass m2, is simply x2, the maximum amplitude, into e to the power I omega t. So we have both. We have, you see, the steady state solution with the x1 p and x2 p, and if we are combining all three, the input and output, then certainly we have simply end up with our main solution matrices minus omega square m plus xp, which is which we want particularly so we have minus omega square m into this one, plus we have, you see, I omega into damping matrices, and then you see we have the stiffness matrix and x part, you see here, and then it is equated to whatever the force is which is being excited. Now our main theme here is to get the homogeneous solution. So for that we need to apply a force factor, and we need to put entire thing equals to 0 to get the eigenfrequency. Since you see in our equation we have the two main factor, one is the damping, one is the stiffness, and if we want the system performance in terms of the eigenfrequency, then first we need to keep the damping factor 0 to get the undamped natural frequency, and if the damping is there, certainly we have the damped natural frequencies. So first of all we need to keep this force equals to 0 to get, because you see the eigenfrequencies are always coming for the free vibration conditions. So the force vector on the right hand side of the equation 1.36 makes an equals to 0, and then in order to calculate the undamped natural frequency, we need to keep the damping factor 0, so that we can calculate the undamped natural frequency. So you see here in general terms, now our equation 1.36 will be equal to minus omega square m xp plus k into xp equals to 0, and it will give you, this equation will give you the undamped natural frequency, the characteristic roots, which is simply reflecting the spring and mass system. Damping on other hand simply brings the complex valued eigenfrequencies. That means, you see here, if we have a mass and spring system, whatever the roots which are coming, which we are saying the characteristic roots or the eigenfrequencies, they are the real one. So we can simply say that when the roots are real, they are simply showing the natural frequency, and the roots are complex values, that means they are showing the damped natural frequencies. Again you see here both the frequencies being there, because our system has the spring and the damping together. So with this particular feature, now if we are going towards first the undamped natural frequency, certainly since the system is having 2 degrees, we have omega 1 and omega 2 as the 2 natural frequencies. Then we can calculate, you see here, minus omega square mx plus kx equals to 0 as we discussed. And to find out these things, as we already discussed, that we need to keep this matrix into the determinant form and makes it equals to 0. Then we have determinant minus omega square m plus k equals to 0, and from that you see here we can simply calculate the natural frequency, or else you see here we can say the eigen frequency, which are nothing but equals to the natural frequency square. So for a 2 degree of freedom system, certainly you see we have 2 omega 1 comma omega 2 as we discussed, or even you see if we are going for higher degrees, this is a pretty we can say the linear terminology for this, that if we have n degrees of freedom system, certainly the n natural frequencies are there for that. So from this part you see here, the since it is a 2 degree of freedom system, so we have the omega 1 comma omega 2, and since it is the motion of the mass m1 and m2, which we are saying x1 and x2, like is being restricted by the spring stiffness k1, k2, k3 according to the arrangement in the previous diagram, we can see that omega 1 comma omega 2 is nothing but equals to the square root of k1 plus k2 by 2 m1, k2 plus k3 by 2 m2, and then you see here plus minus square root of, this is simply like an algebraic equation, and from the algebraic equations we can get alpha 1 comma alpha 2. For that, the similar manner you see we can get this one. So it is nothing but equals to this square root of k1 plus k2 by 2 m1 plus k2 by k3 over 2 m2 is plus minus square root of the whole square, this one. So it is k2 square minus k1 k2 minus k2 k3 minus, you see here we have k1 k3 divided by 2 m1 m2. And again you see here these eigen frequencies are simply giving the the real, we can say, the mode of this one, because this is undamped frequencies, and the real roots are always you see like simply showing that how the variation of the masses are in terms of like the relative positions. Means you see here means if one mass or two masses are in phase or out of phase, and you see here these things in which you see the in phased or out phased are there, we are saying these are the eigenvectors or the mode shapes of this one. So these eigenvectors are mutually interdependent, as I told you, the orthogonal feature, and contain the information that how the system oscillates in the vicinity of their respective eigenfrequencies. So for that, either if we are talking about the omega 1, the first natural frequency, or if we are talking about the natural frequency omega 2, we can simply find out the relative displacement of their masses. And the mode shapes x1 and x2 can be straightway obtained by substituting these frequencies into the main equation, which simply corresponding, say that you see in the equation 1.40 minus omega 1 square mass matrix plus k, this the displacement matrix equals to 0. So these like the displacement for omega 1 we have x1, and similarly you see if we are going for omega 2, the next natural frequency or displacement vector is x2. So minus omega square m x2 plus k x2 equals to 0. So in these two equations you see we know that there is a like the coupled equations, like we can simply get those values x1 and x2 in relation to these variation of the masses and the natural frequencies. So certainly we can calculate the mode shapes from these two. Now we would like to apply this concept into the real application. So you see in the example, this example which is there on your screen, simply a machine is mounted on the elastic foundation. This elastic foundation is not only providing this support, but at the same time it is a kind of isolator to prevent the vibration transmission to the ground. So you see here if you look at that, what we have a mass which is being like creating some kind of motion, and through this motion you see here we have the oscillatory vibrations in that, and these vibrations are being like just transmitted vertically downward. So that you see what we have you see the base, and with the base on and in between the mass we have some kind of you see like the damper or the spring. So if you look at that, the mass m is like we can say it is in the motion. So this mass is something we can say m2, which is at the x2, and similarly you see here the mass m1 is our base feature. You see look at that part, this base, and this base is also, since it is coming under like this oscillatory mass, so it is also having some kind of displacement variation. So x1, so m1 x1 from the base and x2 m2 x2 from the mass is having, you see, makes the equation or makes the system in 2 degrees of freedom. And on below of this mass, this base, we have, you know, like the damper and the spring. We can say this is simply a isolator just to prevent these things. So with this formulation, we can say we have the double elastic mountings in between the mass and the base, and then you see here these are simply providing both the stiffness and the damping together for that. So suppose that you see this machine, which we are saying that is representing by these two. So on top of that, whatever the oscillatory mass is there, it is M2 and the base is M1, and the force, you see, whatever the force which is being excited or being applied, this F excitation force is having the circular frequency of F. And our main theme is to reduce the amplitude vibration which is being transmitted through to the ground through this part. So we can incorporate the spring mass and the viscous arrangement in that. So now certain parameters are there in this. We have the mass M1 and M2 as 100 kilogram and 500 kilogram. The stiffness is also given to as 5 into 10 to the power 6 Newton per meter for first spring, and second is 1 into 10 to the power 6 Newton per meter. Similarly, we have the damping feature in this, you know, like the dV1, that is, you see, the damping in between, you see, the base to the foundation, that is, you see here 100 kilogram per second, and D2, that is, you see, in between the base and mass is 200 kilogram per second. So we have a perfect isolator in between, you see here, mass to the ground in the 2 degrees of freedom system. The main theme is to calculate the undamped the natural frequency or the eigen frequency, in which you see here the vibration frequency, that means, you know, like just generated by the machine which is being mounted on the system, and second, what the mode shapes are. Since we are interested in undamped one, so certainly we would like to reduce the effect of these dampers. So we need to keep mathematically the damping matrix equals to 0. So the system is undamped one, and then you see here whatever the undamped systems are there, only the effect of this is mass and the spring together. So we have, you see, whatever the roots which are being coming out in the equation from this mass and spring system is our undamped natural frequency reflection. So you see here, and then whatever the corresponding eigenvectors are there, they are the mode shapes. So in this figure, you see here, we know that since the damping is there, but we just want to ignore the effect of the damping to calculate the undamped natural frequency. So for that, we already discussed that for undamped natural frequency, we could easily calculate omega 1 and omega 2. In the previous example, we discussed that it is nothing but equals to the spring stiffness variation and divided by the mass. So when we are doing these things, you know, like we have omega 1 comma 2 is nothing but equals to square root of this 60343 and square root of 1657, or else you see it is almost nearly equals to 39.1 hertz and 6.48 hertz. That means we have a clear feature that the first natural frequency and the second natural frequencies are like that, 6.48 the first one and 39.1 is the second natural frequency. And the system's undamped mode shapes can also, you see, like be easily calculated using the homogeneous system equations with the circular frequency Fc for each eigen frequencies. That means what do we have? We have, you see, the omega 1 and omega 2, and whatever the displacement which will coming out from these, say 6.48 hertz and 39.1 hertz, are simply showing that how the mass displacements are there. And then you see we can easily figure out these things by putting this part into the main equation. So the first equation what we have, since the first natural frequency is 6.10, so we can keep that, you say 6.10x, that then you see whatever 1 point like this 10 to the power 6, that is my stiffness, you see here, into x2 minus, you see whatever the damping features are there, 100 omega square this x omega n square x1 equals to 0. And similarly we can keep this part as 1 into 10 to the power 6 into x1 plus, you see here whatever we are keeping the other terms, like you see, like we have the stiffness term at k2 and this mass 500, when we are keeping and we are making equals to 0, we can calculate the mode shapes in terms of, you see, the displacement x1 and x2, which simply indicates that how the masses are being deviated. And by multiplying these things, we can see that it is nothing but equals to -1 into 10 to the power 6 minus 100 omega square, omega n square divided by 6 into this, and when we are calculating this, we could easily figure out that how the masses are being displaced at first natural frequency 6.48 or at second natural frequency 39.1 hertz. And substituting these numerical values in this, we could easily figure out these eigenvectors, and it becomes identical to these like things that when we are evaluating those things, it is a very symmetric process, and this means that you see both the equations are linearly depending, and in the complete arrangement they are simply giving the relative displacement in phase and out phase in terms of the mode shapes. And a linear dependent system with two unknowns has simply you see the infinite number of solutions along with that. So, you see here in order to solve these equations, certainly we need to apply that what exactly like the numerical data which can be incorporated to get the final solution in terms of x1 and x2. So, when we are trying to solve these things, now we are keeping say we can simply put that in terms for this x1 amplitude we can keep alpha 1, and in terms of like x2 we could simply find out that you see x2 is nothing but equals to 1 into 10 to the power 5 divided by you see here 1 into 10 to the power 6 minus 500, which was you see the mass m2 omega n square alpha. And if this amplitude x1 has the value of you see the omega n, then certainly we can say that the x2 must be having the value which simply 1 into 10 to the power 6 divided by this numerical digit. So, what we have now, we have you seen like the eigenvector which is simply corresponding the first natural frequency omega 1 in these terms, where the alpha is simply a constant. An eigenvector is nothing but you see a vector which is specifically in a specified direction, like in phase or out phase. And we could easily figure out that what exactly the x2 by x1 is, what exactly the ratio of that, which simply represented with the variation of this alpha 1. And then when we are keeping those values in this, we could easily say that now we have omega n which is equals to omega 1, and you see whatever you see which is reflecting phi 1 over minus 0.034, and omega n which is simply for a second natural frequency is phi 2 is nothing but equals to 1 over 5.8. So, if you look at these values, we know that in the first one omega 1 we have the mass placing is in the opposite direction. So, orthogonal feature or out of the phase. Second, both are the positive values, you see 1 oblique 5.8, that means you see here we have in phased mass and they are absolutely moving together. So, the interpretation of these like the first eigenvector for like this is the system is excited by the eigenfrequencies just near the first we can say eigenfrequency, and it's simply like we have the resonant conditions of the amplitude with you see the second mass is always being reflected with 0.034 times of the first one. So, the second mass is you see more and more oscillated at the resonant frequency, and the minus sign is simply indicates that both are in the opposite phase as we discussed. So, you see here this diagram this example simply showed that we have a clear kind of like the arrangement, and these arrangements are simply showing that you see whatever the constraints are with the systems, always the masses will be in phase or out phase with any degrees of freedom systems. And now if you are going with any arbitrary number of degrees of freedom, means you see here if we are going to any real life examples, we know that the system is very complex. Maybe you see here right now we were simply formulating the equation of motion based on a linear propagation or linear motion, the axial motion. But if you see the band is there, or if any twist is there, or any elongation is there in two different directions, then certainly the mass which is being distributed is not the discrete one and can be assumed to any of the different models. And then the entire elasticity is straightway disturbed by that. We cannot take you see the linear propagation of the spring as we discussed in the previous cases, because there is certain non-linearity is there due to the geometric feature. So, in the reality we have infinite degrees of freedom in the system, but for our convenience, because we just want to analyze the system performances under the dynamic action. So, certainly what we are trying to see, we are trying to put the finite degrees of freedom system in that, and the methods of modeling which is simply like putting all together, is always depending on what exactly the computational facilities are, and accordingly we can go for the degrees of freedom systems. So, you see here right now we discussed about the 2 degrees of freedom system. So, even we can go with these 2 degrees in the various configurations. So, like on your screen you can see that we have one diagram which simply shows that if we have the springs in the series formulation, that means you see here we have say M1, M2, M3, M4 and all the n masses are being arranged in such a way that all the spring and the dampers are coming in the series formulation. Like you see here for M1 we have K1 and C1 on left hand side, and on right hand side we have K2 and C2. So, for movement of M1 is straightway reflected or straightway you see deviated from this path, and similarly you see for mass M2 is straightway affected by these constraints C2 M2 on left hand side, C3 M3 on other side, and up to you see if we are going up to nth mass, then certainly we know that on left hand side we have the spring stiffness Kn and this damping is Cn. On right hand side we have Kn plus 1 and Cn plus 1 of the spring 1, and with these you see here cascaded masses, all these series solution or the series arrangement of the mass this spring and damper is giving a perfect resolution of the forces, means the damping and the restoring forces along with the inertia forces of the mass. And say if we want to arrange these masses along with the masses or the damper and this stiffnesses along with their own forces, then we can say that first the equation of motion becomes, for the first type of arrangement it is mass m1 into dx1t over dt square, d2x1t over dt square plus c1 dx1t over dt plus you see here whatever the damping which is in between, that means you see here we have the C2, and this C2 is you see here coming in between dx1 by dx1t by dt minus dx2t by dt, and similarly you see here we have both K1 which is absolutely related to x1t and K2 which is related to the difference of this x1t minus x2t. And then you see here since the force is being applied on the mass m1, so you see on right hand side we have the forcing factor. And similarly you see here we can easily formulate all these equations up to the nth mass, because ultimately this is a discrete system in which the system motion is absolutely constrained by these springs as well as the dampers part. So, when we are simply configuring all these forces, we can apply straight with the Newton's law to individual masses, and we can get you see all the force balance equations for that. So, you can see that even for M2 or Mn minus 1 or even for Mn, we have all these you see like the arrangement of the individual forces, like from you see this Mn d2xn by dt is d2xn by dt square. So, this is my inertia force for nth mass. This is my damping force. As in a left hand side you see here we have dxn over dt, on right hand side you see here we have Cm, and this is all the differences of this dxn by dt you see here, and minus you see dxn minus 1 by dt, and similarly you see the stiffness variation like for Kn or you see Kn whatever you see the displacement differences are there for this, and the displacement individual is coming together. But these are the individual equations which are simply reflecting that there is a force balance equation for individual masses, and all this setup under these excitation is under the static equilibrium even after the forcing F1, F2 or F2, Fn or X1 or Xn displacements are there. So, now you see here we can straightway go, because it is a multiple degrees of freedom system, we can go to our like the metric systems, and we know that there is a straight formulation for that. Like for mass, the mass matrix should be identical along the diagonal feature. So, you can see that on your screen the equation 1.46 is nothing but the mass matrix in which all the elements along the diagonal is symmetric, right from M1, M2, M3, M4 and then Mn along the diagonal, and all other elements are simply the balanced equation. Since it is balanced equation, so it should be 0. Similarly for damping, We know that you see when we are talking about the nth degrees of freedom system, there is you see the diagonal feature must be positive. So, you look at that we have C1 plus C2 starting from this and ending up to Cn plus Cn plus 1. And then you see the corresponding feature, if you are just on the first part, means the first mass, which is the motion of the first mass is constrained by both C1 and C2. So, what we have C1 plus C2 on your screen, you can see equation 1.7, C1 plus C2, other side minus C2, and for if you are going towards the mass M2, then you have minus C2, C2 plus C3 and minus C3. Similarly, if you are going towards further directions, we can simply find out that all the damping parts are coming exactly in the positive manner when we are moving along the diagonal of that matrix. And if you are going now towards the stiffness part, it has a similar feature, because the arrangement of the damping and the stiffness is the deformation in the stiffness and the velocity in the this damper, they have in the similar manner. No nonlinearity is there. So, along with that you see the elements in the matrices are also the symmetric along the diagonal feature and they must be positive. So, with that you see we can see the stiffness matrix K1 plus K2, similarly K2 plus K3, plus similarly you see if you are moving towards you see the nth part Kn plus Kn plus 1. So, this entire symmetricity is simply showing that this is a well balanced equation, and they are showing that the entire system is in equilibrium manner, where the non-zero element not shown in the equation are simply marked with the dot and the zeroed value elements are marked with the A in these equations like that, in these matrix elements. And one can even allow the masses to be coupled in parallel, like you see now if we just want to arrange our masses in a different configuration, like you see, like you can see that in this configuration we have the masses. So, the first mass M1 is absolutely okay with our K1 and C1, but you see the masses M2 and M3, they are absolutely coupled with now our these K2 and K4, and this is coupled with K3 and this is my K5. So, when these masses are now coupled parallelly, we can see that there is a clear impact of these coefficients in the matrix formulation or the equations of motion, because now we have a parallel coupling of the masses along with their stiffness and this damping coefficients. And then later on you see if you are ending up with our you see M4 mass along with our K6 and damping coefficient D6. So, when now if we have this arrangement, we can again see that you see what exactly these forces which are being balanced by this F1 on M1, F2, F3 and F4 on these M2, M3 and M4 masses. And when it is so, then you see here the equations are like that. For the first masses there is no change as such you see here, because this is what it is, you see the M1 and this one. The damping here is somewhat changed, because whatever the damping, if you look at the previous diagram, whatever the damping is coming for this first mass is an integral feature of this first K2 and you see the K3 or the stiffness, and the damping is coming from this D2 and D3 here. So, we need to calculate accordingly. So, if we are going towards that, you know that the first CV1 is coming with the dx1 by dt, there is no problem in that, it is a straight damping force. But as far as you see the CV2 is concerned, we have dx1 and dx2 the differences, and similarly for here it is dx1 and dx3, because you see here on right hand side there is a clear interaction of x2 and x3 velocity vector. And similarly if we are going for our stiffness matrices, the stiffness like we can see the restoring forces, then again the restoring forces on the left hand side we have a straight K1 x1, but on the right hand side we have the K2 and K3, they are in the integral feature of x1 x2 and x1 x3, which and then you see we are making equal. So, only what we need to see, we need to make a free body diagram in such a way that how the forces, the restoring forces or the damping forces are coming on mass M1 from left hand side or from right hand side. And once we are making balance of these things, then we could easily figure out that under these force balance conditions there is you see like whatever the mass is, whatever you like the oscillation is there in the masses with the M1, M2, M3, M4, that could be easily figured out. So, now if you are going towards the other masses M2 and M3, so for M2 we know that since the M2 is moving with x2 only, so the inertia force has no problem, but the damping here, the damping force is something you see integrated with x1 and x2 part here, and here it is x1, x2 and x4 part. So you look at that, you see here, this is something here, we have K2 and K4, see this dV2 and dV4, and this both the part you see here straightway affecting the motion of this one. Similarly, if you are coming to M3, we have you see the K3 and here we have the K5, here we have dV3 and dV5, which are simply making the entire balance of this M3. So with this you see here, if you are trying to see the relative motion or the relative effect of this part, you see here, like we can say the damping forces or the restoring forces, all the forces are being resembled here in a proper way. Similarly, for mass M you see 3, which is again the independent masses here, we could easily figure out this part, and M4, which is the separate part, the last part you see here, here on the left hand side of this M4, we have a clear interaction of the two main spring. This is from like the fourth and the fifth one, and also you see here we have a clear interaction on the right hand side, we have the this like whatever the springs are there, like you see here, what are the spring forces are there from the 6 and dV6 from the damping forces. So you see here all these features are being straightway incorporated here. Now if we are just going towards the masses, that how the mass matrices are being arranged along with the masses which are being placed in the equations. So you can see that the mass matrix is again the same, M1 to M4, since the 4 masses are being there. So we can see that since it is a 4 degree of freedom system, and we have like the mass matrices, it is again the diagonal, it is symmetric along the diagonal one. And now if we are going towards the other features like the damping matrices, we can see that even in the damping matrix, right from the first one, because you see the first feature of our like the M1, which is straightway affecting by 3 damping forces. One dV1, the damping coefficient on left hand side, on right hand side there was a straight effect of dV2 and dV3. So this part is straightway you see coming here, we have dV1, dV2 and dV3 all together there, and on the other side we have, since like there was you see a clear dissipation on the right hand side, it is minus dV2 and minus dV3 on the other features. Similarly, if I am going towards the other part, it is minus dV2 which is being there, and then you see in the middle of one, since it is being straightway, we have the two main part on M2, one on this like dV2 and dV4. So certainly you see the featured all the featured will come into the main part dV2 and dV4 here, and similarly you see all the diagonal feature is, you see it is positive and they are being arranged in this way. And since you see as per the like the damping feature, the stiffness, the spring is also arranged in same way. So we have the spring, we can say coefficients are K1 plus K2 plus K3 as far as you see the left and right hand side of M1 is concerned. And similarly, if you are going up to the nth part, we have K4, K5, or up to the 4th mass, we have both K4, K5 and K6 for this one. So in this also we could easily figure out that even you see here whatever the arrangements are, the general principle for generating these matrices for the system in which you see the direction of forces and the velocities are defined in this one can also be summarized in this way. First, the mass matrix must be diagonal. That means you see here like whatever you see, even the masses are arranged in the parallel way or the masses are arranged in the like we can say the coupled one, the series one, just you see in the first case which we discussed, the mass matrix must be diagonal. So this is one of the thumb rule for that, and or else we can say it is a checking point for this. Second, the diagonal element in the stiffness matrix or the damping, because you see here both the spring and damper is arranged in such a way that they are absolutely like occurring in the similar manner as far as the restoring force or damping forces are concerned. So the stiffness or damping matrix is sum of the spring rates or the damping coefficient respectively of all the springs and the dampers connected to the mass indicated by the row number of elements. That means you see here even the first mass, as just in the previous case which we discussed, the first mass either in the series feature, if it is being constrained by K1 dV1 or K2 dV2, or else in the second case where the coupled one is there, the parallel one, if this M1 was like on left hand side it was K1 and dV1, or on the other side it was K2 dV2 and K3 dV3, but their arrangement, whatever the coefficients are coming, they are coming exactly along the diagonal feature, that what exactly the contributing like these forces or the elements are. And an off diagonal element at a specific row or the column position in the stiffness or any damping matrix has an opposite or negative value of the spring rate or damping coefficient respectively. For that, the connection between the masses simply indicate by row number and that indicated by the column number. So, what does it means that? It means that whatever you see the off diagonal elements are there, at any row you see here, they are simply giving the position of any spring or the damper features by the negative way, minus dV2, minus dV3 in the first part, or even the second feature, the second row when it is starting from the second like element in the first column, minus dV2, and then you see here the other things are coming dV2 plus dV3. So, what I mean to say that in these like or either we are in the 2 degree of freedom system or multi degree of freedom system, the arrangement of the elements in these matrices are a pretty standard one, and this is what you see like making a thumb rule for like all these arrangements of the elements in a perfect positions in the matrices. And it is even you see like a checkpoint for this, that if like the things are not coming in these ways, that means either the forces are not properly configured or there is some problem in calculation features, or in degree like when we are just doing like the free body diagram, we are not able to characterize properly. So, you see in this today's lecture we discussed mainly about that, you see like if we are talking about the 2 degree of freedom system or multi degree of freedom system, does not matter, only we need to see that how these forces, because this is a discrete system, so how the forces like the inertia forces are being balanced by the stiffness force, this restoring forces through the stiffness of the spring, or the damping forces through these damping coefficients. And when all these being under balanced condition, even like the force excitation is there, then what exactly the like the elements are being arranged in the matrices, because we are now playing with more degrees of freedom system, the multi degree of freedom system. So, there was a straight rule which we discussed already, that in the elements either we are talking about the mass matrix, either we are talking about the stiffness matrix or the damping matrix, how the elements are being arranged in a proper way. So, you see here in these 4 lectures till date, we were just discussing, it was a like it all these lectures were the review feature, because you see here ultimately our main theme of this course is to control the vibration, the vibration control. So, until unless if you are not able to characterize the vibration properly with the single degree, 2 degree or multi degree of freedom system, then we cannot say that we can effectively control, or we can even effectively adopt any control strategy for these systems. So, in the next lecture now, our another feature will start, the second module, that simply shows that how we can control the vibration. So, first of all we would like to discuss in the next lecture that you see what exactly the formation of vibrations in the different systems for a mechanical machinery, how we can strike on the root cause of vibration, and once you find out that yeah this is my cause of vibration, then how like what kind of control strategies are there, because ultimately like in the vibration the 3 main features are there. First, the source, second the receiver and the sink, and you see the transmission, means what is the path of that, the transmission feature. So, you see here where do we need to put the isolators. In the passive vibration control, in active vibration control, the first thing is there, strike immediately on the root cause of vibrations. So, in the next lecture we would like to discuss the aspects of control of vibration, okay, along with the transmission, the root or the means the source or the sink of that. Thank you.